Hello everyone, I am Dr. Rabia Kamra and I welcome you all to the first lecture of Sequence and Series. In today's lecture, we will discuss about sequences and their convergence and divergence. The content is taken from the book Calculus and Analytic Geometry by Thomas and Finney. Now, let us see what is the literal meaning of sequence. So, a literal meaning of sequence is a particular order in which the related things or objects or numbers or strings follow each other, right? And when I restrict myself to the sequence of numbers, we can say that sequence is an ordered list of numbers. So I'm saying order in which the numbers are appearing is important, and that order is defined with the help of some rule. Now, a sequence is a list of numbers in a given order. A1 is the first term of the sequence, then A2, A3, and we keep on going like this. An denote the nth term of the sequence. Now, this sequence could be finite or infinite. If it is finite, say it has n terms, then I say that the number of elements in the sequence is n, and n is the length of the sequence. And if there are infinitely many terms, we say that we have an infinite sequence. Remember that order is important. Okay, now let us see this one. The first term of the sequence is 1. Second term of the sequence is square root 2. Likewise, the third term and the fourth term is given. Now you have to give me a formula for writing the nth term of the sequence, or the defining rule, the rule which defines the nth term of the sequence. So I can say that the nth term of the sequence is square root of n, and I denote this sequence as this one. Okay, here the nth term will be 1 by n. What about this one? Nth term will be 1 by n, but you have a positive term, then a negative term, positive and negative. So I can write minus 1 raised to the power n plus 1. So when you substitute n is equals to 1, you'll get the first term of the sequence. When you substitute n is equal to 2, you'll get the second term of the sequence, and so on. Likewise, here the nth term would be where the denominator is 1 greater than the numerator. So in the denominator I have n, in the numerator I have n minus 1. Now you substitute n is equals to 1, you'll have first term 0, n is equals to 2, you'll have 1 by 2, and this one. Likewise, this one is called a constant sequence where nth term is also equals to 3. So what we see over here is that I can say that I have a function a of n which is equals to some rule. Say for the first example it is square root of n, wherein I am substituting the values of n, 1, 2, 3, 4, and I'm getting some output. Okay, so I am trying to relate the sequence here with a function which has a domain 1, 2, 3 up to so on, and correspondingly I am getting some output square root 1, square root 2 to so on. And the rule is that a of n should be equals to square root of n. But here n is taking only the discrete values. I can say n is, you can say n is a set of natural numbers. Or if I say my sequence is of the form this one, square root 3, square root 4 up to so on, then I can say I have a sequence an where n varies from 3 to infinity, or I can say this one square root n where n varies from 3 to infinity. Now I think you are ready to see the mathematical definition of a sequence which is related to functions, which says that an infinite sequence of numbers is a function whose domain is the set of integers greater than or equal to some integer n naught. Why this is coming? I'm saying that you have this domain, you have a function and you have this output, the codomain, the range. Here I am saying 1, 2, 3 up to so on, and here I am getting some output as per the rule, say A of n. Now here I can say the domain is set of natural numbers, or I can say the domain is set of positive integers, or if your sequence is such that it is 1 by 9, then 1 by 10 up to so on, in that case I'll say it is 1 by n, where n varies from 9 to infinity. So I can say that the domain is the set of integers starting from 9 till infinity, right? So that is why I'm saying the domain is a set of integers greater than or equals to some integer n naught. So in this case, my domain is integers greater than equals to n naught, where n naught is 9. So this is a generic definition. Okay. Now you have to find a formula for the nth term of the sequence. So first few terms of the sequence are given to you, and you are expected to write the formula for the nth term of the sequence, because whenever I want to see the behavior of a sequence, nth term of the sequence is an, I want to see that whether this sequence is converging or diverging or anything, then I must know what is the expression for an, what is the underlying rule. So from this sequence, write an. So an should be such that every even term should be 0 and every odd term should be 1. So every even term will be 0 if I'll have minus 1 plus 1, this is giving me 0, and here if I say minus 1 raised to the power n, when n is 1, it is giving me 0. So no, I should put n plus 1. So when n is equals to 1, I will have minus 1 raised to the power 2, that is plus 1 that is 2. Let us divide it with 2. Now try to find a1 with this formula. A1 is minus 1 raised to the power 2 plus 1 by 2, that is 1. Then a2 is minus 1 raised to the power 3 plus 1 by 2, that is 0. And a3 will be again 1, a4 will be 0. So this formula satisfies these terms of the sequence given. So this is the rule, or this is the formula for the nth term of the sequence. Okay, now let's try to write the nth term of the sequence for this one. Now we have repeated integers, so 0 0, then 1 1 1 three times, then 2 2 2 three times, and 4 4 4 this time. So whenever you have this type of a sequence where you have repeated integers, try to apply floor function or ceiling function. So floor function is when I have say 0 1 2. If I am here somewhere, then the floor function of 1 by 2 is 0. You have to move towards left. Floor function of 1 will be 1. Floor function of 1.3 will be 1. Floor function of 2.9 will be 2. This is how the floor function is defined. Now let's try to write the formula for the nth term. So my n will vary from 1, 2, 3, 4. Let's try to write the floor function of n by 2. So floor function of n by 2, that is 1 by 2 will be 0. So I have 0 here, 1 here, 1 by 2 here. The floor function of 1 by 2 will be 0. Floor function of 2 by 2 will be 1. Floor function of 3 by 2 will be 1. Floor function of 4 by 2 will be 2. So I'm not getting that order. I have 0 once and 1 twice, but I wanted 0 twice and 1 thrice. So here, let's try with, in place of n by 2, take n by 3. You know, if I take n by 3, then I will have 1 by 3, 2 by 3 as the first and second terms, and they will go to 0. See, the floor function of 1 by 3 will be 0. The floor function of 2 by 3 will be 0. The floor function of 3 by 3 will be 1. That is what I wanted. So I am going as per the order. I should get till fifth term. So for third, fourth, fifth terms, I should get 1. Third, 4 by 3 के लिए भी 1, then 5 by 3, 1. Yes, and when I have sixth term. So 6 by 3 will be 2. So this is fine. This works well. So the nth term, the formula for nth term of this sequence is the floor function of n by 3. Okay, now let us see how do we graph the sequences. When you have a sequence of numbers, you can always uh, plot these numbers on the real axis. This is one way of doing it, one standard way of doing it, that you have this number, say your sequence is an is equals to square root of n. So you put n is equals to 1, you have first number on the real line, then the second term of the sequence is a second dot on the real line, then the third one, fourth one, and you keep on going like this. You'll have these numbers. And the second way of doing it, rather than plotting this thing on the real axis, you can plot it in the coordinate plane. So in the coordinate plane, you plot these points n, comma an. So on the x-axis, you have n, that is the domain, that is the first term, second term, third term, and on the y-axis you have an, the value of the first term. The first term of the sequence is 1, so you have this point 1 1. Then the second term is square root 2, so this is 2 comma square root 2. Then the third term is 3 comma square root 3, and this way you can plot this. Okay, now let us see what is the convergence and divergence of a sequence. Then again, the literal meaning of convergence is, converge means tend to meet at a point. So when you are tending to meet at a point, I'm saying a point, not 2 points, okay? Then we say that this is something called convergence. And when you are increasing indefinitely, going off to plus infinity or minus infinity, or you are not going towards a point, you are going towards more than one, say 2 points, this is literally diverging. Okay, you say the roads were diverging, right? So converging means when you are tending towards a point, and diverging means moving apart, going away. Okay, now let us see, for this sequence, when your an is equals to 1 by n, let's try to sketch the sequence both on the real axis and on the coordinate plane. So the first term of the sequence is 1, second term of the sequence is 1 by 2, third term of the sequence is 1 by 3, and the terms are decreasing. As your n is increasing, your 1 by n is decreasing, and you can see that the limiting case, when you'll have the limiting case, your n tending to infinity of an, where an is 1 by n, what will be this one? This will be moving towards 0. Jitna n bada hota jayega, you will be moving towards more and more closer to 0. Okay, so we can say that this sequence an, or this sequence 1 by n, converges towards 0. Now let's see it in the coordinate plane. When you have the first point, as when you are sketching n comma an, so the first point is 1 1, second is 2 1 by 2, third is 3 1 by 2, 3 1 by 3, 4 1 by 4. So as your n is increasing, these points are going to become closer and closer to the x-axis, yet not touching the x-axis. So I can say that this sequence of points will be such that this line x-axis, that is line y is equal to 0, is a horizontal asymptote to the sequence of points. This is just an observation right now. Okay, we are not concluding it. I just want you to observe it in each example, that whenever you have a case of convergence, when your sequence an is converging to this number L, this will happen if y is equal to L line will behave as a horizontal asymptote to the sequence of points. Okay, now see this next example, where I can write my nth term as 1 minus 1 by n, and the limit of this one as n tends to infinity an is equals to 1. And we see it graphically as well. Your first term is 0, your second term is 1 by 2, third term is 2 by 3. So terms are increasing. You see that a3 is greater than a2, right? A2 is greater than a1. This is happening. But this term, the nth term, is always bounded by 1 because n minus 1 is less than n, and n minus 1 by n will be always less than 1. So you see that this is the point where your whole sequence is going to accumulate or converge. Okay, and you can see it on this coordinate plane as well. You have these points, and you see that these points will be such that they become closer and closer to this line as n tends to infinity. And see this line, what is this line? Y is equals to L, where L is 1. So again, an is tending to 1, an sequence an is converging to 1 if y is equals to 1. This line is acting as a horizontal asymptote to the sequence of points. Okay, now see next example where you have alternately positive and negative terms. So in the previous example, this one, I was reaching towards this point 1, which happened to be the limit of the sequence from one direction. Likewise, in this example, I was moving towards 0 from one direction. But sometimes it is possible that you move towards limit from both the directions. It is this example when you have positive 1, so you are here, then negative 1 by 2. So you hop towards the left hand side of the axis. A2, then A3 is on the right hand side but little closer to 0 now. Then A4 is minus 1 by 4 from the left hand side, more closer. So you see that you are going close and close to 0, but one term is coming from the positive x-axis and the other from the negative x-axis. You see, when you take limit of this one as n tends to infinity for minus 1 raised to the power n plus 1, 1 by n, this limit will go to 0. That is not a problem. But your even terms are all which are lying on the left hand side, and your odd terms are all which are the positive terms which are on the right hand side. So eventually you are converging to this point because whole of my sequence is moving towards one point, and that one point is 0. So I say my sequence is converging. And see, in the coordinate plane you have first term 1 1, second term 2 comma minus 1 by 2, third 3 comma 1 by 3, fourth 1 4 comma minus 1 by 4, and as your n tends to infinity you will have terms closer and closer but coming from both the directions now. Okay, both from the positive side and negative sides. And again you see that this line y is equal to 0 will act as the horizontal asymptote to the sequence of points. So far we have discussed the examples in which you have the case of convergence. Like in this example also, you see this is a constant sequence which happens to converge. Now we will discuss the cases when you have the case of divergence. Now see this one, the nth term of the sequence is square root of n. So the first term is here a1, second term is a2, and you see a2 is greater than a1, then a3 is even greater than a2, and it's that an is greater than the previous one. So I'm just moving away, or I am increasing indefinitely. As my n increases, the terms of the sequence become increasingly large, and I cannot say that they accumulate towards any point. They are not going towards a point. So this is the case of divergence, and in the coordinate plane also you can see these points will keep moving away from this one, or I can say they are going to increase and increase, right? There's no bound to it. So this is one way of diverging when the things or the terms of the sequence are becoming increasingly large. And the other case of divergence is when they are not becoming increasingly large, they are bounded, but they are not going towards one point, they are going towards 2 points. Let us see this one. When you have the nth term is minus 1 raised to the power n plus 1, 1 minus 1 by n. Okay, now you see your first term is 0 here, the second term is minus 1 by 2 here, the third term is 2 by 3 here. So you are moving away from 0, right? And eventually Your odd terms are lying on the right hand side, even terms are lying on the left hand side. All the odd terms are moving towards this number 1, because when you take the limit of this one as n tends to infinity, this will tend to 0. So eventually this whole thing will converge to, when I say limit n tending to infinity an, when you try to take this one, you'll have two things. When your n is odd, so this is minus 1 raised to the power n is odd, so odd plus 1 is even, so this is positive 1, so this will tend to 1. When your n is even, n plus 1 is odd, so this is negative coming from here, and since n is tends to infinity, this is 0, so this is minus 1. So when your n is positive and even and odd, your sequence terms of the sequence are moving towards two different points, right? So sequence is moving towards two different values, but this cannot be the case. I am saying converging means you will go towards one point. There is one point which you are moving towards, not two different points. This is the case of divergence. So we have discussed divergence in two ways. In previous example, when my n was increasing, I was saying that an is also increasingly large. But here they are not increasingly large, they are still bounded in here. But one term of the sequence are moving here and the half of the terms are moving here. Okay, so this sequence is also diverging, but the reasoning is different. That's what I want you to understand. Okay, and you see in this coordinate plane, this line is y is equals to 1, this line is y is equals to minus 1. So you see you have again two asymptotes too for this one, right? But that cannot be the case. Okay, now see this example when your an is equals to n minus 1 by n or 1 minus 1 by n. Now I want to give you the mathematical definition of convergence or divergence of a sequence. For that, to get the essence of that, I just want you to observe this sequence in the terms of the sequence. So this is the first term of the sequence, that is 0, that is here. Second term of the sequence 1 by 2 here. As we keep on moving, as we keep on increasing our value of n, we are going closer and closer to 1. And here, as you are increasing your n, you are moving closer and closer towards this asymptote, right? But how close to 1? If I say, if my n is increasing, say my n has increased till 100, then I am saying I am going closer towards 1. And if my n has increased to 10 to the power 6, then also I am going closer towards 1. But of course, if my n is this large, I am much more closer to 1 than in this case, right? That I want you to understand. So see this one. If I have moved first term, second term, if I have moved till 10 terms, my next term is 0.909, which is close enough to 1. But if I have moved till 101 terms, my value is 0.9901. Means I am much more closer to 1 than this one, right? So I can myself choose that how close I can be to 1 depending upon how many terms of the sequence I am going towards. If I am considering the terms of the sequence, 100 terms of the sequence, I am close to 1. But if I say I am going till 1000 or 2000, I will be even more closer to 1. So this is how I want to define here the definition of convergence. I am saying that I can, this is my term an, I can put this term an very close to this one, where 1 happens to be the limit of the sequence. I am saying that this an in converging to L. So I can make this difference of the terms of the sequence of this limit L, I can make this difference small enough as much as I want. If I want to say कि the terms of the difference, the terms of the sequence and the limit should be less than zero point 0.1, difference should be less than zero point 0.1, I can say, okay, go till n greater than 10 and you will have this difference less than zero point 0.1. But if I say no, I want the difference of the terms from the limit L to be less than zero point 0.01, it means I have to move more greater terms. If my n is greater than 100, in that case this is less than zero point 0.01. So you can see from here that I want the difference of an from L less than zero point 0.1. So an is 1 minus 1 by n, minus L is minus 1, minus 1 cancels out. So 1 by n is less than zero point 0.1, means n is greater than 10. So difference of an from L is less than zero point 0.1 if your n is greater than 10. Difference of an from L is less than zero point 0.01 if n is greater than 100. Means if I want to make this difference of an from L less than epsilon, where epsilon is very small quantity, I can see that how many terms I should move, and I am representing this as capital N. Now I am defining that a sequence an converges to a number L if to every positive number epsilon there corresponds an integer n, such that for all n, when small n is greater than this integer capital N, the difference of an from the limit L is less than epsilon. Okay, so I'm saying that this sequence an converges to L when for every epsilon, so epsilon ये role play कर रहा है, epsilon is playing this role. I can make this epsilon as small as I want, and I will have this corresponding capital N for every epsilon greater than 0. Okay, for every epsilon greater than 0, I will be able to find a stage that after that stage an is very much close to L. So an converges to L if to every epsilon, for every epsilon, I can tell you a stage that go till this integer. Beyond this integer, difference of an from the limit L can be made as small as you have chosen epsilon. Okay, so this is that stage, that after this stage जितनी भी terms आएंगी sequence की, they are going to fall into this difference. So an minus L is less than epsilon is greater than minus epsilon. So an will lie between L plus epsilon to L minus epsilon, and this is for n greater than capital N. And that capital N I will find out this way, that this is my capital N, this is my capital N. Okay. Okay, so after this stage, the terms of the sequence are lying within epsilon distance from this limit L. Okay, I am saying that the terms of the sequence are lying within epsilon distance from L. Okay, if you are able to find such an L, we say that the sequence converges. If no such L exists, we say that the sequence diverges. If sequence an converges to L, we will write this way, that limit of an as n tends to infinity is L, or we simply write that an tends to L and call L as the limit of the sequence. Okay, I hope that we are making sense so far, because this is quite important. I want to say that this sequence will converge to L if after a stage I can put the whole tail of the sequence, I am putting the whole tail of the sequence into this interval. If I am able to do it, I can say my sequence converges. Means पूरा का पूरा tail should accumulate towards this limit L. And this is on the real axis, and on the coordinate plane it will look like this one. This is my L, this is L plus epsilon, this is L minus epsilon. So after this stage, all the points of the sequence are going to lie within this band, within this L minus epsilon to L plus epsilon. Okay, and you can see that when an tends to L, this y is equal to L will behave as the horizontal asymptote. This we have already seen with the help of some examples. And also we can say that all the points of the sequence after this stage will lie within epsilon distance of L. Right? This means the distance of an from the limit L, and this distance is less than epsilon after a stage. और normal plain language English में कैसे बोलेंगे, that the tail of the sequence is lying in this interval. Okay, now let us see an example. Show that minus 1 raised to the power n plus 1 and n minus 1 by n, so this is 1 minus 1 by n. So you have to show that this diverges. We have already seen it with an example. Now with the definition we have just given, I can just say that the odd terms are going towards 1, even terms are accumulating towards minus 1, but I cannot find a single interval so that the whole tail can lie within that interval. So neither the epsilon interval about 1 nor the epsilon interval about minus 1 contains a complete tail. Okay, this is important. I cannot say that a part of the tail is in 1 and a part of the tail is accumulated about minus 1. This is not convergence. Convergence means I should get a single value and whole of the tail of the sequence should lie within epsilon interval from this single value L. Okay, so convergence or divergence of a sequence has nothing to do with how the sequence begins. किससे लेना देना है? It depends only on how the tail of the sequence behaves. If you are able to put the tail of the sequence into an epsilon interval about some number L, then you can say that L is the limit of the sequence. And here in coordinate plane also you see you'll have a band over here and a band over here. But none of the band contains the whole tail of the sequence. Okay. So with this, you should be in a position to solve problem number 1 to problem number 22 from the exercise 8.1. Okay, thank you very much.